So we have a meter stick that has a horizontal frictionless tabletop pivoting around the 80 centimeter mark. So I'm going to mark that as my rotation axis. A force F1 is applied perpendicular to the meter stick as shown at 0 centimeters, and a second force, not shown, is applied perpendicular at the 100 centimeter mark on the stick. So I know that I'm going to attach a force 2 at that point. Forces are all horizontal, so that means this force 2 can be in any of these directions, but it has to be in that plane. If the stick does not move, the force exerted by the pivot on the stick is what? Wow, this is a kind of a crazy question. So they want the force exerted on the pivot by the stick. So what is the force? It's a normal force at the pivot points. Pivot points up, and it's going to be pushing normally on the stick. Well, I know that two things have to happen in this case. I have to have the net force on the stick to be 0 and the net torque on the stick to be 0. So the net torque is actually the first one I'm going to start with. If the net torque is equal to 0, I have to figure out what my torques are. Well, I know that I have force 1. It's at distance 1. So force 1 at distance 1 points, it's perpendicular to each other, so I have the sine of 90 degrees, or 1. And it's going to point in the my D cross into F, it's going to point into the page. I'm going to label a normal coordinate system, X, Y, and Z comes out of the page. This is a minus Z direction. This second force has to balance it out. So I know I need a plus sign, and I know D2 is going to point in this direction from the axis of rotation to where the force 2 is attached. So if I need a positive, that means my Z has to be out. So D cross into F has to be out of the page. So I know force 2 is going to be perpendicular of some way. This is going to be probably the easiest thing that I can come up with for this case. So I get D2, F2, that should be F1, is equal to 0. So I have that. Do I give myself a force? So this just says that F1 D1 over D2 is equal to F2. Just rearrange that to the other side and divide by D2. So I have a relationship between F1 and F2. And I know that D1 is equal to 80 centimeters and D2 is equal to 20 centimeters. So D1 is 4 times larger. So F1 is 4 times smaller than F2. D1 is 4 times larger than D2, so F1 is 4 times smaller than F2. So let's start looking at some of our answers and see if we get some stuff. Must be 0. Well, I have two forces pointing in the upward direction, which means that I need some normal force to cancel that. And I know that it has to have a magnitude of, well, if I have F1 pointing up in the y direction plus F2 pointing up in the y direction, that means I have to have my normal force pointing down to get 0. So I know my normal force points down, or F1 plus F2 has to be equal to my normal force. This whole section is using Newton's second law for translation, or F equals ma, which means that if I substitute in, that means this is 5F1 is equal to my normal force. All right, so must be 0. No, I know that my normal force is not 0. This pin is going to keep this thing from sliding upward. Must be in the same direction as F1. Well, no, it can't be in the same direction as F1. It has to be opposite of F1. Again, I can cancel out D because of that. Must be in the opposite direction of F1. Okay, that's good. And have a magnitude of the magnitude of F1 plus the magnitude of F2. So I see that choice E is the right answer. My magnitude of F1 plus magnitude of F2, they both point up. That's what's canceling the rotation part, but the pin is canceling the translation part. Both of them point up. The pin has a force that points down.